Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on nonlinear control systems. Today we are going to continue our discussion on nonlinear controllability and observability. Last time we discussed the accessibility and controllability for nonlinear systems, and today we are going to discuss the observability for nonlinear systems. So what is observability? Observability is calculation of the ability to be able to calculate state vector from the information about input and the output of the system. So input of the system is something that you apply to the system with the calculations. So you already know about the input. The output of the system you can determine from the sensor values, and from these signals, if you are able to construct or reconstruct the initial state vector, which means that you will be able to construct state vector for any time t in the past, then the system would be considered as observable with the sensors that you have employed in the system. So observability for linear systems, you already know that for a system x dot equal ax, y is equal to cx, where x is a n dimensional state vector and y is p dimensional output vector, where p is less than n, which means that you are not measuring all of the states, but you are measuring some of the states. So from the measurement of some of the states, if you are able to determine all of the states, then the system is observable. And how do you know whether some of the states would be enough or not enough? That you can know by calculations. Specifically, you can determine the rank of observability matrix, which is C CA square up to so on CA raised to the power n minus 1. This matrix has P times n rows and n columns. So maximum possible rank of this matrix is n. If the rank of this matrix is n, then that means that the system corresponding to these C output matrix and A system matrix, that system is observable. Okay, so this was a review of observability for linear systems. For nonlinear systems, we need to discuss the concept of Lie derivatives, and for the concept of Lie derivatives, we first need to revise the concept of gradient. So gradient of a smooth scalar function h of x of a vector x is given by del of h is partial h by partial x. So this is partial h by partial x1, partial h by partial x2 up to so on partial h by partial xn minus 1, partial h by partial xn. So this is a vector which is derivative of a scalar with respect to each component of a vector. So this will be 1 cross n vector. Similarly, if there is a vector field f which is Rn to Rn, then its gradient with respect to x will be given by a Jacobian matrix, which basically is partial f1 by partial x1, partial f1 by partial x2 up to so on partial f1 by partial xn. So this will be the first row. The second row will be partial f2 by partial x1, partial f2 by partial x2, and up to so on. So this is the each row is the derivative of a particular component of this field f with respect to all components of the vector x. So similarly, the last row would be the partial derivative of the last component of f with respect to each of the components of the vector x. So this is called Jacobian matrix. So these are the gradients of scalar and vector fields. And now we come to the Lie derivative. So let us suppose we have a vector field and a scalar field. Then the Lie derivative of h with respect to f is a new scalar defined by L sub f of h is equal to del h dot f. It's basically a dot product between two vectors. Del of h is a vector, as we have seen in the previous slide. F is also a vector, as we already know that this is a vector field. So when you take the dot product of two vectors, that is a scalar, and this is sum of all the component wise product of the vectors, the two vectors. So you can also write this in matrix form like this. So Lie derivative of h with respect to f is the del h vector times the f of x vector. So when you multiply this vector with this vector, the result will be a 1 cross 1 scalar. Okay, so higher order derivatives, well, the d derivative that we have discussed in the previous slide can be referred to as the first order Lie derivative, and the zero order Lie derivative of h is h itself, and first order Lie derivative is del of h dot f. Then second order Lie derivative is the Lie derivative of the first order Lie derivative with respect to f. So this is the first order Lie derivative of h, and if you take the Lie derivative of this Lie derivative with respect to f, then that is second order Lie derivative. And then similarly you can take the Lie derivative of any order by taking the Lie derivative of the previous order with respect to f, and you can continue on in this manner. So what is the relevance of Lie derivative with respect to dynamical systems? Consider the input output system x dot equal f of x and y is equal to h of x. Then the derivative of h of x with respect to time, that is given by partial h by partial x into partial x by partial t. This is chain rule. So this partial h by partial x is nothing but del of h, and partial x by partial t is x dot, which is f of x. So h dot is equal to del h dot f, which is very familiar to us, which is basically first order Lie derivative of h with respect to f. So you can see that the Lie derivative of so with respect to input output or dynamical systems, the Lie derivative of the output with respect to the dynamics of the system is same as time derivative of the output. Similarly, if you take the second order time derivative of the output, that will turn out to be second order Lie derivative of the output with respect to dynamics of the system. So this is the relationship between Lie derivative and the input output dynamical systems. Okay, so now we move on to the observability condition for linear systems in terms of Lie derivative. So you can we can say that there is a linear system x dot equal ax, y is equal to cx, and x is rn vector, n cross 1 vector, y is p cross 1 vector. Then let h of x should equal to c times x. So in that case h of x will be a vector which will be a vector of p components, just like y, because y is equal to cx and y is a p cross 1 vector, so h will be equal to y, which is p cross 1 vector, but we have defined h equal to c times x. Similarly, let's define f of x equal a times x, and that will also be n cross 1 vector, which will be equal to the derivative of x. If we define h of x and f of x in this manner, then the first order Lie derivative of h with respect to f, that would be partial h1 by partial x1, partial h1 by partial x2. This should be x2 here, there is a mistake. Then partial h1 by partial xn, and similarly partial h2 by partial x1, partial h2 by partial x2, and so on, partial h2 by partial xn, and up to so on. This will be the del of h. So del of h times f of x, that will be Lie derivative of h with respect to f. And if you take del of h, we don't have to take del of h in this manner. We already know that if h is c times x, then del of h will be just c, because that is the derivative of c times x with respect to x. Alright, so since f of x is equal to a times x, then and del of h is c, so L, the first order Lie derivative would become c times a times x, because f of x is ax and del of h is just c. So this is the first order Lie derivative of h with respect to f in the linear systems that we know. So then again I continue this discussion on the next slide, where h is c of x and f of x is a times x. Then the zero order Lie derivative would be c times x. That's simple. And then first order Lie derivative would be c times a times x, and then the second order Lie derivative would be c a square times x. And you might already have guessed where I am going with this. So n minus 1 order Lie derivative would be c times a to the power n minus 1 times x. So you can see that we already have the observability matrix, but this observability matrix is multiplied with the state vector x. So if we take the derivative of this whole, if we put all of these Lie derivatives into a vector and then call it the let me do that on next slide. So let's define G to be a vector of all the Lie derivatives. So each of these Lie derivative itself has multiple rows and columns, so this is not just a vector, this will be a matrix. So if we take the derivative of G with respect to x, so if we take the del of G or dg or delta G, whatever you want to call it, so if we take del of G, then this will be del of each of those, and del of each of those, what will happen? Like if you take let me go back to the previous slide. So if you take del of cx with respect to x, it will be simply c. If you take del of this will be c into a, del of this would be c into a square, and del of this would be c into a raised power n minus 1. So you can see that taking the del will basically, this will be the observability matrix. So del of G would be the observability matrix, and the rank of observability matrix we already know determines the observability for linear systems. So this is how Lie derivative is related to the linear systems and observability of linear systems. And you can also see that G, if you want to reconstruct G, then del of G, you multiply del of G with x, then you get the G back again. So think of dg as the gradient of G. Okay, so the observability matrix is basically nothing but dg, and it must be full rank for observability. So this way we have rewritten the condition of observability of linear systems in terms of Lie derivatives. So next we are ready for nonlinear systems. So consider a nonlinear system, x dot equal f of x comma u and y is equal to h of x. Then h of x could be anything, a p cross 1 vector, where h1 of x could be a nonlinear function of x, h2 of x could be another nonlinear function of x, hp of x could be another nonlinear function of x. But all of these nonlinear functions should be smooth enough so that we could take derivative with respect to x. Alright, so for this nonlinear system, two states x0 and x1 are distinguishable if there exists an input function u star such that the output corresponding to u star for the initials for the state x0 is not the same as the output due to the control input u star and the state vector x1. So if the output corresponding to two state vectors is not equal to each other for a given input, then these two states are distinguishable. So if there exists an input, means there, even if there is a single input, like maybe these two are same for some of the inputs, but there exists at least one input u star such that these are not the same, then we would say that these two states are distinguishable. The system is locally observable at x0 if there exists a neighborhood of x0 such that every state in that neighborhood of x0 other than x0 itself is distinguishable from x0. So if all the states in the neighborhood of x of 0 are distinguishable, have different outputs compared to the output corresponding to x0 for at least one of the input functions, then the system is locally observable. So this is the definition of local observability. If you think about this definition, so this definition is basically helping us to determine the state vector, because if we know that output due to every state vector is different, then from the output we can determine which of the state vector this output belongs to. So please try to understand this point, that if every state gives us a different output corresponding to an input u star, then using that output we can determine which state should have resulted in this output. So which is the original definition of observability that we saw in the first slide, that the observability is the ability to calculate or determine the state vector from the output value. So if outputs are distinguishable, then from each output you can go back to you can trace it back to the corresponding state vector that is causing this output or resulting in this output. Okay, so test for local observability of nonlinear systems. So this is the definition of observability, and now we are going to look at the conditions under which we could say that the nonlinear system is locally observable around any point x naught. So consider a nonlinear system x dot equal f of x, the same nonlinear system y is equal to h of x, where h of x could be a p cross 1 vector of nonlinear functions. Local test for observability in the neighborhood of x of 0, that is the matrix O, which is a function of x of 0 and some control input u star. That O matrix is the same DG matrix that we defined previously, that it is the gradient of the Lie brackets, the Lie derivatives. It is the matrix of gradients of Lie derivatives of the output with respect to the dynamics of the system. So if you expand this matrix in terms of components of H, then this is the zero order Lie derivative of H1 up to so on zero order Lie derivative of HP, and this whole thing will correspond to C matrix in the linear systems, but in this case the H1 up to so on HP are nonlinear functions, and then this is the first order Lie derivative of H1 up to so on first order Lie derivative of HP, and then up to so on first order Lie derivative of you can take like second order Lie derivative, third order Lie derivative, and up to so on n minus 1 order Lie derivative of H1 up to so on n minus 1 Lie derivative of HP. So this would be your observability matrix for the nonlinear systems. So number of rows in this matrix would be p times n, just like in the linear systems, and number of columns in this matrix would be n. So maximum possible rank of this matrix would be n, and if this matrix is full rank, then we would conclude that the nonlinear system is locally observable about the point x naught. Okay, so this matrix must have rank n. Note that O is the gradient of the vector of Lie derivatives, just like the linear system case. Okay, so let's look at an example of observability for nonlinear systems. Let's consider the system x1 dot equal x1 square over 2 plus e to the power x2 plus x2, and x2 dot equal x1 square and y is equal to x1. So this is the nonlinear dynamical system. In this system you can notice that h of x is just simple x1. So del of h would be partial h by partial x1, which is 1, and partial h by partial x2, which is 0. And then f of x is basically the first component of x. F of x would be the derivative of x1, which is x1 square by 2 plus e to the power x2 plus x2, and the second component of f of x would be the derivative of x2, which is x1 square. And if we take Lie derivative of h with respect to f, that would be del of h, which is this 1 0 multiplied by the vector f. And if you multiply 1 0 with this vector, this will be just 1 times this component plus 0 times this component, which will result in simply this component. So Lie derivative of h with respect to f would be the first component of f, which is x1 square by 2 plus e to the power x2 plus x2. So let's look at the observability matrix in this case. So in this case the G matrix would be L, the zero order Lie derivative and the first order Lie derivative, because we only need the derivative to be n minus 1 order. So here n is 2 because there are two states, so n minus 1 is 1, so we only need to go to up to the first order derivative. So zero order derivative of h is h itself, which is x1, and the first order Lie derivative of h is, we already have calculated that, it is x1 square by 2 plus e to the power x2 plus x2. And if you calculate the O from this G matrix, then you have to take the gradient. So gradient of x1 with respect to x, that would be partial x1 by partial x1, which is 1, and partial x1 by partial x2, which is 0. And the gradient of this thing with respect to x would be partial of this whole thing with respect to x1, which would be, if you take the partial derivative of this term, this will be 2x1 divided by 2, which is simply x1, and partial derivative of both of these terms with respect to x1 would be 0. So the whole thing, partial derivative of this whole thing with respect to x1 would be simply just x1. Similarly, the partial derivative of this whole thing with respect to x2 would be e to the power x2 plus 1, and this is now, this dg is the gradient of G, which is the O matrix. And so since there is no U function here, we don't have to define any U star, and so far we are not evaluating it we can evaluate this O matrix at any x0. So x0, remember that we calculate the observability locally at some point x0. So whenever we have to find observability at any point x0, it will have the components x01 and x02. In place of x1 here, we will put x01, and in place of x2, we will substitute x02, the second component of x0 here. So but in this case you can see that no matter what x0 we choose, for all the values of all possible x0, for all possible values of the state, the rank of the O shall remain 2. You can see that because there is a 1 here and there is a 1 here, so this is a diagonal, like these two regardless of the values of these x2 and x1 terms, the rank will always be 2. So in this case, this system is observable for all x of 0, and that is one example of how you calculate the observability for nonlinear systems, and this system is locally observable everywhere. Okay, so this concludes the discussion on observability of nonlinear systems and the discussion of today's lecture as well. We have already discussed the nonlinear controllability, and today we have discussed the nonlinear observability. So this concludes the overall topic of nonlinear observability and controllability as far as this course is concerned. But of course, this is just the beginning. This is just your foundation for the concept of controllability and observability for nonlinear systems. You can go a long way with this foundation, and you can build your knowledge upon this. And briefly, I would just go through the lecture again. In the beginning, we looked at the definition of observability, which is the ability to calculate state vector from input and output. And the observability for linear system, we revised this condition that this matrix, if it is full rank, the system is observable. If it is not full rank, the system is not observable. And then we looked at Lie derivatives, but before we looked at Lie derivative, we looked at the concept of gradient, and we looked at the gradient of a scalar function as well as the gradient of the vector fields. And we saw that the gradient of a scalar function is a vector, and the gradient of a vector field is a Jacobian matrix. And then we looked at the Lie derivative. The definition of Lie derivative, it is just the scalar dot product between the gradient of one vector field or a scalar field. This could be a vector field or a scalar field. There is no restriction here with another vector field. And then you can represent this in matrix form as well. And Lie derivative itself is a scalar. So you can also calculate the higher order Lie derivatives by taking the Lie derivative of the lower order Lie derivatives. And then the relevance with the dynamical systems, how Lie derivative is the time derivative of the output of a dynamical system. And then we looked at the observability condition for linear systems in terms of Lie derivatives. We defined h of x equals c times x and f of x is equal a times x, and then Lie derivative was just c times a times x. And we looked at the Lie derivative of all the orders. We stacked them together, and we saw that this is something very similar to the observability matrix. So if we take the gradient, if we define the G matrix to be the matrix of Lie derivatives, then the gradient of G matrix is nothing but the O matrix, which is the observability matrix. So this must be full rank for observability. So then we finally discussed the observability for nonlinear systems. We saw that two states are distinguishable if their corresponding output is not same for at least some input function. And if all the states in the neighborhood of a state x0 are distinguishable from that state x0, then we say that x0, the nonlinear system is locally observable around x0. And then we looked at the test for observability for nonlinear systems. That was this observability matrix, which is very similar to the one in linear systems, except that here the h1 and up to so on hp are nonlinear functions, so their gradients will be different from simple c. Okay, so then we looked at an example of nonlinear system, and we calculated the observability by calculating first the Lie derivative matrix, and we took the gradient of the Lie derivative matrix, which gave us the observability matrix. And we saw that observability matrix has rank 2 for all x, so we say that system is locally observable everywhere. So that concludes the lecture. I hope you were able to understand the concepts, and if not, let me know about your questions or concerns. Thank you for listening.